Hello everyone, welcome to Engineering Bakar. Today, me, Baljit and Vivek will discuss HyperLogLog. So HyperLogLog is used to solve big data approximation problems. So let's understand what is HyperLog. So HyperLog is a probabilistic algorithm and it is used for estimating the cardinality of a large data set. So let's say if we have a website where we have to count the unique number of users that are visiting our website for a particular day or for a particular month, or let's say for a particular year, or from the lifetime of my website. Now, one way could be to record everything and then do it via database, and then we get the 100% accurate result because I'm counting it in my database, but that is very memory intensive. We have to store a lot of data. And this is where HyperLogLog comes into the picture, and it is a very optimized way which is able to give you that cardinality in a large data set by doing the approximation. Use cases where it is used. So one is unique visits on the website, or similar problems are unique users that have played a particular song or unique users who have viewed a particular video. So all these use cases that you will see on the social media, more or less they might be using this approximation. Why we are saying approximation is because it has some error and that is very low. So that's why it's approximation. It's not an exact count, but it is able to give you the very good insights into the actual number, and it is very optimized solution. So that's where it is used a lot. So let's say we have to count how many unique visitors are there in a particular exhibition. How would you do it? If we think in the database kind of model, typically what would you do is you will record the name of every person that is visiting. Name again can collide, but let's say that even if the names are unique, effectively you have to write down all the names of all the people, which will require a lot of pages, and then effectively then you will do the counting, right? And let's say if you might record one name multiple times, so you have to handle with uniqueness. Apart from name, another thing could be, let's say, because name has collision. So what is other unique way? You can, for uniqueness, you can take last 6 digits of their phone number. We are assuming it's not a very big exhibition and there are people around in the range of 10 to the power 6 or something. So you can take down the last 6 digits of the phone number and then count the unique phone numbers to get the approximate number of people that are there in the exhibition. But in both the cases, you will see that you need large number of data to be stored. In this case, you'll be writing on the pages, and you will need a lot of pages to write down all the numbers, and it will take a lot of time and a lot of effort. Now, if I ask you, can you achieve this task just by finger counting? Is it possible? Answer is yes. And this is where this Flazell-Martin algorithm comes into the picture. So what is the idea behind this algorithm? The algorithm has a simple idea which says that I just have to keep track of what is the largest sequence of leading zeros I have seen till now. If my last 6 digits of the phone number are these, in first case, there's no zero. So my answer is 0. In second case, I've seen 1 0. Third case, till third case, I've seen 1 0. That is the largest. And let's say till the end, your longest sequence number of zeros is 2. Then this algorithm simply says that approximately I have seen 10 to the power X number of people, and that is my estimation. So for the large data set, this will perform much better. And this you can do on your finger counting. So this is one of the basic idea of the algorithm. This is not the exact algorithm. Given a data set, you just need to keep track of leading zeros. And based on leading zeros, you will be able to evaluate approximate number. So instead of counting the zeros in decimal, this algorithm works on the binary data. So effectively, for every data set, because every data set will not be a binary data, will not be a numeric data set. For every data set, we will have a hash function. that hash function gives a binary output, and in that binary output, we will count the leading zeros.
So what exactly do you mean by finger counting? Just by looking at the data, we should be able to tell.
Finger counting is basically counting on your fingers that rather than using any data set, can you count the unique visitors on your fingers?
Okay. Okay.
Okay.
But
So,
that would be limited by the number of fingers you have, right?
right, but in this case, if you see, right, if I have, let's say 10 fingers, I can count up to 10 to the power 10, because I just have to keep track of leading zeros that I have seen till now. I will just say I have seen 2 zeros. So current my finger counter is 2. Then if I have seen 3 zeros, I'll say my finger counter is 3. That is the only thing that I have to change. Only the counting is changing. I just don't have to remember anything that I've and about the numbers that I've seen.
So, is this based on some sort of observation or some logic? कि क्यों अगर finger count अगर मैं zeros count कर रहा हूँ, right?
Yeah.
Decimal में zeros का track रख रहा हूँ.
Correct.
Let's say I see only up to 2.
Okay.
Then I'm saying कि 100 customers आए होंगे.
Correct. Because you have seen only 2 zeros, that means that all the numbers were in the range of, let's say, 00 to 99. Right? Which is an approximation saying that you have seen only 2 leading zeros, so mostly you have seen 100 people at max. But let's say if you have seen 101 people, there are high chances that you will end up having 3 zeros. If everyone has a unique phone number.
Okay, everyone has a unique phone number. Okay, then
in that case, there's a high chances that if you have seen 101 phone numbers, there will be at least 1000 in the phone number.
Correct.
Correct. So that's why this algorithm, what it says is, I will just keep track of the leading zeros that are there in the particular phone number that I'm seeing.
So the question I have is how did we discount the scenarios? See, why does this Flazol-Martin algorithm, why does it work? Because
it is a probability thing, right? That it is guessing the number of people you have seen based on probability.
So my question is probability point of view. Say, what's the probability that all the 100 customers that came, unique customers that came, they had no zeros?
So see, effectively, you can find a data set which will not have any zero in the leading data set. But assuming that if the data set is fairly distributed in terms of equally distributed, right? That there's no bias in the data set, then you will end up finding the approximation. So this is just the idea, right? See, so this slide is just talking about the idea. We'll get to the approximation, like how the actual approximation works.
Okay.
This is just saying that if you have seen 1000 numbers, then there will be chances that you will see at least one number with 4 zeros. So that is where this approximation is coming.
That I got. वो समझ में आ गया. And that is basically the basis of behind this algorithm.
Correct. But in the phone numbers case, based on geography or based on a lot of things, the data might be biased.
And this is applicable for any digit, right? Zero is a random. We chose zero randomly, right? There's no significance.
In this case, we are seeing zero. This algorithm works on the binary numbers where 0 and 1 are the only choices, right? So they picked 0 as a candidate, right? That counting zeros. You can also say counting ones. It will work equivalently.
Okay.
Okay. So effectively, it says that if I've seen L zeros, 10 to the power L is my approximate number. This is the idea based on probability, but let's see how the actual approximate number is counted.
Okay.
Now, since one thing that we have talked about is my hash of data is.
Where did hash come here?
So why did hash come? Because I have to uniformly distribute the data. Like if I talk about the phone numbers might not be uniformly distributed. If I have function which can distribute this data uniformly, then this probability approximation will work much better. Now, as of now, we are talking about numbers, but here we are saying that any data set, any large data set you take, find a way to hash it to a binary number.
Okay.
Okay. Now, based on the leading zeros of the binary number, you can say that how many leading zeros you have seen. So what is the probability that a particular number has 3 leading zeros? It becomes like 1 upon 2 to the power 3, right? Right. So
in this case, in this data set.
In this data set. So effectively it says that if you have seen X number of leading zeros, then 2 to the power X is your approximate number of people that you have seen. So this algorithm, first thing is we need to use a hash function, and second is it generates a binary output, and based on the digits that you're seeing, we say that how many people we have seen. So for a data, for if you have seen, let's say L number of zeros, then this algorithm says approximately 2 to the power L people you have seen. But there is a correction factor concept. So in the published paper, they talk about a correction factor, which is about this 0.77351. And the cardinality based on this algorithm is 2 to the power L divided by this factor. So this is the approximation, which was the first proposal by this algorithm.
So cardinality is the actual unique value?
Correct.
So what we'll do is, in this particular case, I saw 3 maximum as the leading digits, leading zeros. That means total number, since we're talking binary, 2 raised to power 3.
Correct.
Is the total number of unique customers, but I have to apply the correction factor.
Right.
So divide 8 by this correction factor.
Correct.
So this correction factor is use case and situation agnostic.
Correct.
Okay.
But obviously, this algorithm has some error. Right? It's not like this algorithm gives you the exact number. So there's some error rate. But let's talk about how to, like, what will happen in this particular algorithm. In this algorithm, we can see, right, if we find if one of the hash value is biased, right? Let's say it can create a bias, because let's say if it ends up generating a very low number for a one particular value. Let's say you get a very first element that turns out to be this 0, 0, 0, 0, 0, 0, 0, 1, 0, basically 7 zeros. Then it will skew your data, right? And then the output that you will get via this algorithm will be will not match your data set.
So hash is very critical here.
Correct. So
even if I have a pretty good unique ID generation algorithm, that might not be sufficient.
Correct. And that is where they came up with another algorithm, which is called LogLog, and which says that rather than using one hash function, you can use multiple hash function and take an average of all the hash functions.
Okay.
So that will ensure that if one hash function is creating a bias, then if, let's say, using the hash function, my minimum comes out to be L1, and then using hash function 2, my minimum comes out, maximum comes out to be L2, then take average of all these values and then use that to calculate the final prediction.
Okay.
But again, since if you use multiple hash functions, then you have to do a lot of computation. So they have another proposal where they are saying that use one hash function, but use first 2 digits to create the bucket. So let's say if you want to use 4 hash functions, so rather than using 4 separate hash functions, create 4 separate buckets, and that bucket is defined by first 2 digits of the output, and the remaining value is used for the prediction. So then first hash value, which is computed for x1, it says 1, 0 is bucket, and then 0, 1, 0, 1 is the value. So I will create bucket number 3, and this bucket number 3 has 1 candidate. Similarly for x2, bucket number 1 has 1 candidate. Bucket number 0 has another candidate for x3, and for x4 there is a bucket number 4 which has candidate. So effectively, whole data set is now divided into these 4 separate buckets, I'll calculate the L value for each bucket separately, and then use those every bucket's L value to do the average. So that way my hash function is 1, but I have divided them into 4 separate buckets, and then I'm doing the average of all the values.
Okay.
So effectively, these are 2 different ways to do the average. And in second example, we are just using one hash function, so it is less compute intensive. And the cardinality of this algorithm says that so we are using the average value of L and then divide by the same correction factor. But then because we are using M buckets, so there's a M into the value becomes the formula for cardinality. So this is, they published another paper with this optimization, and they talk about that the standard error rate of this algorithm is 1.3 divided by root M percentage.
Sunny, just a quick thing. See, even in this case, we initially started with the problem, right? So the problem is the data set is huge. And if you want to, let's say, find out the number of unique visitors, let's say on that, you have to basically, if you do not have all this, you basically have to do the counting in the code, which is resource intensive, right?
Correct.
However, in this case, we are basically going via this particular thing where we are dividing into buckets and then counting the number of leading zeros and dividing into then doing an average of by hashing it with another function, right?
Right.
Isn't it again doing some computation on all the values? Then how is it better than going through all the values?
So see, in a database set, you will need to store all the items and then use some database query to get the data, the average. Then effectively you are storing everything into the database. But in this case, you just need to keep track of one integer, right? This L value. And I don't need to store all the L values that I've seen till past.
That is correct.
So in terms of that, I don't need to store too much data. I just need to keep track of current L value. That's it.
No, certainly that's true for the normal counting as well, right? So you can simply maintain a counter as well in the system instead of use Redis or something else. Whenever a new customer logs in, you just a new ID is generated, right? You can just add that counter.
But how do you know if that's a unique thing or not? To identify unique, you need to know, right, that if you have seen this particular thing in past or not.
So I think the problem statement, the trade-off, and in what scenarios this kind of approach is needed or actually helps is where the gap seems to be. I think
problem statement is uniqueness. Like, we are not saying I have to just count all views or all visits, right? I have to count the unique. I think the term unique is a highlight here. I have to count the unique visits on this particular page or unique users that have played this song.
So why does the normal counting not work? The normal approaches on do not work in this for these problems is because we need to do some computation and rely on some sort of querying.
And I get the Sunny's point. So I think Sunny, let me try to phrase it, and then you correct me if I'm wrong. See, if we keep a counter, then the counter does not have any information if a user has visited once or it has visited twice. Even if I, let's say, visit a page, it increments the counter. I visit the page after 20 minutes, it will again increment the counter because it does not have any information about me visiting the page. Now, if we want to calculate the unique visit in the right way, the right way would be that we store that information, who has visited what page at what page somewhere, and then do a counting of that, and then only we'll be able to arrive at this number. Sunny, is that correct?
Correct. So basically, in database, for every user, you will need to keep a record, and you need to check if that is a unique or not for every visit. And if it is unique, then store it. Otherwise, basically, you can just update something and then do a count star or something, right? And then
so just to clarify, we need the context that we need to have to actually count or arrive at the unique number without any probabilistic algorithm is it's a trade-off or is an overhead that will not be able to
Correct. So I think we'll look at the pros and cons of this algorithm, right? So in a very large data set, you might have to store terabytes of data just to get the unique visits. But using this algorithm, you can do it in few KBs of data.
It's an extension of what previous algorithm was.
Correct. So basically, the author started with this basic idea and then extended it to LogLog, which is using the multiple buckets, and then did another improvement and came up with this SuperLogLog. And what the author says is basically, if you throw out the largest value that we got from each bucket and take only 70% of the smallest values, then all the bias that might be getting created will reduce, and then the error rate reduces to this 1.05 divided by root m percentage. So that's just another proposal that author gave. And using this algorithm, so everything else remains same. Only thing is we throw out the largest 30% of the values. Theoretically, the error of this algorithm is 1.05 to the divided by root m, which is less than the previous version, which is 1.3. But the problem that I see with this algorithm is that you have to keep track of all the values and figure out which is smallest, which is largest, which again beats the purpose of this algorithm, right? So that's where the final version of this algorithm comes into the picture, which says HyperLogLog. And this is near optimal cardinality estimation algorithm, which is that instead of using the geometric mean to average the result, use the harmonic mean, because larger values is what create the bias, right? So finally, the author figured out if they use the harmonic mean, which is doing the reciprocals and then doing the mean, taking the mean, then it gives a better result. And using that, the cardinality formula becomes like this. And instead of geometric mean of 2 to the power L, now it becomes like harmonic mean of all the 2 to the power L values. And then standard error comes out to be lesser than the previous algorithm, 1.04 divided by root m. And it's saying like the computation wise, it is not very compute intensive. So this is a final algorithm, which is used by a lot of systems today. And it is used to approximate count in data sets when we face these kind of problems that I have to count the uniqueness in the data set. So pros wise, it has a very low memory footprint as compared to the database approaches, very fast computation, and scalable for real-time big data applications. And on the con side, it cannot be used where you need exact counts, because there is an error margin of around 1%, 1 to 2% based on which algorithm you are using. And there are other implementations also which has now developed after this algorithm, which are more accurate. So depending on your business use case or how much error you can deal with, you can use these algorithms. In the real world, databases also provide a default implementation within DB, where Redis has commands using which you don't need to implement the algorithm. You can just use these commands to maintain the data sets. It will automatically compute, and it has the functions which give you the approximate count. Similarly, Cassandra and Postgres also gives these HLL functions by default. So you don't have to implement the algorithm as such. You can directly use these commands using the either Redis CLI or Redis SDK. Now, analytics platforms like Google Analytics and Mixpanel also use HLL for counting unique sessions. So if you're using Mixpanel, then mostly HLL is being used internally, which gives you the unique session count for your application. All the network monitoring tools which exist, right? Not all, but most of the tools might be using HLL internally for flow measurement. Like let's say if your load balancer has to count the approximate number of connections that are incoming for a uniqueness. Like again, the unique word is the highlight here, that you have to count the unique number of connections that it has received, number of unique IPs or number of unique devices. So for that, these network monitoring tools internally might be using HLLs. So there are a lot of places where this is inherently used, and it gives a very good approximation of the data and view of the overall system. So let's look at how we can use Redis to out of the box to implement this. So Redis HyperLog implementation internally uses up to 12 KB of memory. It says up to because for smaller data sets, it will use small memory, and as the data set grows, it can use up to 12 KB of memory. And then it provides a standard error rate of 0.81%. And using these commands, we can use Redis to approximate this. So pf add is one command where you can create a set. Bikes is a set here, and then you are adding these 4 items into the bike set. So using pf add, it will create a set, and these 4 items are getting added. And now if you do the pf count, it will give you that approximate output at how many unique items exist in the set. And then pf add, you can create another set. So you can create as many as separate hyperlog counters. So this is another commuter bikes where you are adding 3 separate values. And then there's a pf merge where you can merge both of these hyperlogs. And then if you do pf count all the bikes, it gives you the output of 6. So
pf add is specifically for using HyperLogLog.
Correct. So pf add is very specific for hyperlog related commands. So these are the 3 commands using which you can do everything in Redis.
What's the recommendation for what kind of datasets should we use HyperLogLog? Does the paper mention anything about the best range?
So looking at the Redis documentation, it says that it uses up to 12 KB and it is able to count up to 2 to the power 64.
2 to the power 64.
Yeah, which is fairly large. But also says that for smaller data sets, it will use less memory, which means that internally Redis is doing some optimization in terms of how much memory it will be used, and then it keeps on increasing the memory based on how many elements you are adding to the set.
So does it mean I can start using this for even smaller data sets?
Yes. So effectively, I think this can be used for small data sets, and there should be some recommendation that how much of memory you should be using based on the problem statement. Like if you remember, right, we discussed Bloom filters, right?
Yes.
Bloom filters also gives some recommendation on how much memory you should be using based on how much error percentage you want, and how many elements I think are there in the set. So based on that, it gives you the how much memory you should be using. So similarly, I think this also should have some recommendation that how much memory we should be using based on the data set's approximate size, and then how much error percentage we want. But in this case, I think error percentage is fixed because of the algorithm, and just the memory varies based on your data set.
Okay. So essentially, by using HyperLogLog, I can remove a lot of complexity in my systems, but only if I can live with the error rate.
Correct. So if you have to just approximate count of values, count of unique values, then this is a very good solution.
Okay.
It is majorly then good enough for analytics purpose only, right? Where there is no non-critical analytics.
Correct.
Anything on which you do not wish to base any transactions or any
yeah, like for a pricing kind of use case, you will not use it because you want to charge accurate pricing. But if you want to get approximate insights into your system, then this could be a good use case.
So insights is a good use case then, basically.
Yeah, correct. Analytics.
Yeah, same thing, right?
This is the equivalent Golang implementation of the previous Redis CLI, right? So basically, Redis client has these methods: pf add, pf count, and pf merge, and you can basically use these SDK methods to manage the data on sets and get the counts. It's a fairly simple implementation. So yeah, that was all about HyperLogLog and the history, how it was developed as an approximation algorithm.
What kind of data as an input can I use for it? For example, let's say I have a I have a system which creates a unique ID for every customer that is visiting my platform or my website, right?
Yeah.
So using that unique ID that my system generates is good enough, or should I be using some other vector like mobile number, email?
See, if you already are generating a unique customer ID, then your system already knows how many customers exist.
Correct.
Right. So, well, I was thinking it's more like, let's say, in a scenario where you don't have the identification, and the
Okay.
only identification that you are using is some kind of heuristic like IP address or something. Let's say, if on your website, when customer are visiting, you can use IP address as a identification that how many unique visits are there, right? So in those cases, I think it is a very good fit. But if you already have a customer ID, then I think you already know how many customers are there in your system.
For funnel view generation, etc., it might be useful that there are 1,000 customers who are logging into my system in a particular time window. But I do not know how many were on the first page, how many went to the add to cart, how many went to the checkout page, right? In those kind of scenarios also I can use it, because with the condition that I have instrumented even for each and every step.
Correct. So basically, then for every step, you will have a separate hyperlog.
Correct. A separate hyperlog counter for each and every step.
Correct. And then you can say that X number of users reached a particular step, X1, X2, X3, and then you can draw that funnel out.
Correct.
That was all about HLL. If you still have any doubts or any questions, feel free to write to us in the comment section. Thank you.
Thank you.